Hello everyone. Today I'm going to deliver a lecture on earthquake resistance design of flat slab. So first of all, I will discuss the flat slab on earthquake, then moment transfer of slab column connection, then lateral deep and punching shear, then reinforcement detailing and flat slab, then shear reinforcement and flat slab, and then integral beam with vertical stirrup, and last one in earthquake resistance design of flat slab or conceal beam. And another topic is earthquake resistance design of steel structure, but I will not discuss today on in this lecture or in this part. Okay, so let's start. Okay, so I'm taking this note from Honorable Professor Dr. Iftekaranam sir, University of Asia Pacific. Okay, let's see. The flat slab are used extensively due to economic and structural system and architectural versatilities. Among its various advantages are faster construction due to simple formwork, no restriction on the positioning on horizontal surface and partition, and a smaller total building height due to absence of beam and better able to resist continuous exposure and fire than beam girder floor due to lack of many sharp concern. Due to this advantage, flat slab has also gained increasing use in Bangladesh over the few years. This has been popularized especially by architect, building and builders owner and developer. So we can see here the no beam or free layout and large window create bright and open space in flat slab floor. There is the no beam in this slab, so this are the flat slab, and the open space and flat slab are the creating bright and larger window. You can see here larger window. So let's see the flat slab in earthquake. However, no attention has been given behavior of the system lateral loading, particularly major zone motion and due to earthquake. This despite in the fact of slab system, there are been major earthquake zone, which is zone 3 in Bangladesh is Sylhet and Mymensingh also, and many building codes and are allowed to the mandatory detailing requirement for the moderate earthquake zone, which is zone 2. These are the provision. These are the region. Their stipulation are apparently not knowing or understood even structural designers, not to speak architectural or building and developer in our country, showing that the collapse of flat slab building in Haiti in 2010. So you can see here collapse of flat slab in earthquake. 1 to B is Haiti. So this is the flat slab is collapse 1, 2, 3, 4, and Mexico City. This is the Mexico City. Um, so we can complete here the flat slab earthquake. So now we'll go to the moment transfer at slab column connection. So let's see moment transfer. The earthquake observation, the experimental testing have shown in flat slab system lateral movement induced earthquake ground motion combined with gravitational pull and slab can make connection between slab and column, and susceptible failure such as failure can causes for entire building collapse, and if significant moment are to be transferred from slab to the column as would result the unbalanced gravity load either side of the column from horizontal loading due to wind or seismic effect in shear stress in critical action is no longer uniform distributed. The situation can be moderate and shown this figure 1. This is the figure 1. V is represent the total particle reaction uh, trans- transferred to the load, and mu is represent the unbalanced moment to be transferred. So this is the shear. We've been seen the total particle reaction has been given, and m is the unbalanced moment. Here is the unbalanced moment. This is the tension and compression and depth. So the zone will be C plus D. This is the very important. So C2 plus D is the punching zone we know. Here is the P1 and BR, and C1 and C2. So transform movement of the from slab to column, the force resisting from vertical load and unbalanced moment. So you can see one is critical section for interior column. This is the interior column we can see here, and shear stress distribution for exterior column. This is the shear stress. Okay. So stress indicate the square. Stress indicate the square column is about 60%. This is the very important. Of the unbalanced moment is transfer of the forces with tension or compression, and 40% stress face the critical section. This is also important. We have to memorize that the test indicate of the square column about 60%, and 40% by shear stress face in critical section. Okay. So for rectangular column in portion transferred by the uh, flexural increase, which is C to D, become the negative larger relative C1 plus D is given here. According to ACI code 1352, the moment considered by flexor, which is MB, this formula will be used for flexor. While the transforming assumed to be transferred by shear ACI code, which is given this formula for square column. Okay, C1 into C2. This equation created 60% of the unbalanced moment transfer. So we have to keep in mind again and again 60% is very important. So unbalanced moment is transformed by the flexural and 40% shear. So we have seen the 60% is taking the flexor. This is also flexor, and 40% shear. According to this available data, C2 is very large and relative to almost entire transfer flexor and the punching shear stress. We have been seen given this formula, where S is the area of the critical section, C1R is the distance from the centroid critical section left and right, CL is left, CR is right face of the section respectively, and JC is important as a property of critical section analogous polar moment of inertia. So this is the important for exterior column. As you will be, we have been use this formula, but polar moment of inertia will be this formula. On the other hand, if the exterior column will use the SE, which is the area of critical section, but the polar moment of inertia will be this. So we have to keep in mind that there are the two formula we have been used here. Okay. So we have completed here moment transfer. Now we're going to the lateral drift and punching shear. So here is the lateral drift and punching shear. The flash slab for slab column frame subjected to lateral displacement due to earthquake, or we can say lateral load punching failure possible even if the shear stress on slab critical section does not accept the nominal stress, and this is no stress induced failure. In this case the hypotenuse, and that is the shear stress kept taken the critical section degraded, and punching failure occurred when the shear capacity degrade due to the point if the equal the demand. This is often referred to the drift induce the failure of the deterrence of the failure stress induced. So we have been seeing here drift ratio versus shear force ratio. the shear strength ratio. Shear strength is given BR, which is the x-axis, and on the other hand y-axis we can see the drift ratio, which is dr. So we can calculate here dr 3.5 minus 5 br. If br is less than 0.6, it will be 0.5 if br is greater than 6. So this is the our graph. So according to SCI 31 code, we can see here the maximum drift ratio or story drift height in present taken in the highest of the stories above below the connection, and the slab column connection may be endure absence of the shear given below. Following the relationship is given, where BR is the shear strength and given by relation, whereas B is given this formula, and another BU is the where BU is ultimate factor, and unbalanced absence of unbalanced moment calculation is given here. So we are completing here. So another is reinforcement detailing in flat slab. So let's see here reinforcement detailing of flat slab. The moment MUV can be UV ultimate unbalance can be accommodated by the concentrating suitable factor of the slab column strip reinforcement near the column. According to SCI code, the steel must be placed within the width between lines 1.5 H on the each side. So 1.5 H on each side of the column or column capital, where H is the total thickness of slab or drop panel. Total width B is with the effective of the effective. Okay, total width of the effective, and it is called conceal beam. So most of the known of the conceal beam is given as so it will be C plus 3 into H. Okay, let's see here another point we have to keep in mind that steel must be placed within width between 1.5 H. Okay, another word if we calculate the width, so this is the important total width of the effective or conceal beam. We are calculating here C plus C means column, and 3 into H. 3 into H. Why 3 into H? Because 1.5 into 1.5, that means 3. That's why C plus 3H. This is the given in figure C plus 3. On the other hand, if we draw figure this, then it will be C plus 3. Okay, this part of will be 1.5 H, and this part of is 1.5 H. That will be 3H. Okay, at least half column strip reinforcement and all reinforcement for moment ultimate balance must be placed here. This is the at least half of column strip reinforcement, and all reinforcement for column must be placed in this zone, which we have called the conceal beam or total width of the effective. Okay, so another note we have been seen here, at least 1.5 of the top reinforcement column strip continue to along the space. This is that. And another we can see, notice here, at least half bottom reinforcement at mid-span carried out the support of the anchor. And another we can see here the at least 1/3 of the reinforcement column strip only we have been used at the top exterior. We can see here all the top reinforcement anchor is here. This is the exterior column, this is the interior column. So this is the reinforcement in region in moderate seismic load. But there is another notice, flat slab are bent in region of major earthquake zone, which is in Bangladesh, Silat in Malaysia. So in this case, I have completed here reinforcement detailing of flat slab. Now shear reinforcement of flat slab. Now we can see here the shear reinforcement flat slab is provided. Flat slab mainly protect from the destructive shear failure. Among the various such option protective and mention of the figure we've been seeing here, the shear reinforcement plus slab is band bar. We can see one here is a band bar. Another is integral beam with particle bar. This is the integral beam with the particle bar. Okay, let's see the band bar reinforcement. So we have been here the shear reinforcement bar is used. The limit nominal is 10 pm. Calculate the critical section d by 2, which is supported face and increase 6 f prime c and bt, where 3 root prime c bt for WSD according to SAI, and the shear resistance which is B, which is 2 root over f times CPT. If we calculate in WSD, then we can use this formula. The total bar area, the critical section will be this formula. And the integral beam with particle we have been seen here. The band bar is reinforcement is not extensive, may be troublesome condition, and the reinforcement in column joint region. Shear reinforcement using vertical stirrup integral beam avoid the much of the difficulty. So you can see the first critical section shear we have been taken divided by 2. So this is the important, as we have been seen in previously critical section is d divided by 2. So we can say this is the important. And the column fashion usually stirrup needed to exit to the outward in column direction until the face of the concrete. So column carry BC equal to 4 into root over f times CPT. And on the other hand, for WSD for this formula. And second critical section within the region of adjacent column, and where the section resistance provide the combination concrete column and nominal shear strength B must not exceed. So we cannot exceed from this formula. If we use the WST, then we can use this formula, and contribution reduction B is using this formula. Okay, so the critical section, each integral beam we can see d divided by 2 measured outward from the last stirrup and is the located in perimeter B not and the typical cases, and define 45 lines between the integral beam. So you can see here shear band and placement around the column. This is the shear band placement around the column. This is the this is used this in this way, because this is the column. And the shear start and applicable in flat slab. So this is the shear start, this is the column, and this is the shear start is used using surrounding this way. The ductile shear reinforcement and punching shear with shear start and ductile reinforcement will be used. This is use region of the column. Okay. So we can now. Oh, sorry. Now in this two case are completed. Now see the earthquake resistance design of slab or conceal beam. This is the last portion of today's lecture. Okay. So we can see here the earthquake resistance design of slab. Let's read. The column are 5 inches, 15 inches into 15 inches in 6 inches thick of the flat slab plate in shown figure is given below. Middle strip is measure AC. Here the measure AC. Each column strip is measure BT are obtained from the bending moment considering all loads, dead load, live load, earthquake, and calculate the weight of the conceal beam and minimum reinforcement with the conceal beam in a long direction, only long direction. So if we see the question here, this is the question. So we can see here AC, the middle strip AC, this is the A and this is the C, and the column strip BD, this is the B, this is the T, because this is the column along the column, there's a column strip, this is the column, this is the column along the column. On the other hand, between two columns, this is the middle strip, this is the middle strip, this will be also middle strip, this will be almost middle strip. On the other hand, this will be column strip, this will be column strip. Okay. Let's see here. The detailing also there is given here. The exterior column entire unbalanced moment is transferred to the edge of the slab for column 12 at the rate of 6 inches center by center. This is found from ETIPS or calculation. The column strip we have been seen here L divided by 4, which is 15 inch divided by 4, and 50 plus 50 divided by 4, which is 3.75, and 3.75, which is 5.7 feet, which is 19 inches. And alteration we can see here area of the 12 millibar we have been found 0.175 inches square. For 6 inches we have been found 0.375 inches square. As we know, we have been used the spacing as into p divided by s and found putting this formula and found 0.315. For 7.5 feet as we have been found, just just multiplying 7.5 feet, which is found we have been seen here. So 2.63 is for full column strip. Now using 12 millibar, so number of bar we have been used 2.63, and we have been using point 0.17, as we have been seeing the 12 millibar and found 15 bar. So we can see the 1512 bar at the top as in the in 19 inch. Now we can calculate the A using this formula. But we remind that the B will be must be 90. How will get the 90? 90 is nothing but it is the column strip, which is divided 4 we have been calculating in previously. Okay. So in this way we can calculate the moment of the column strip also. As usual we have been putting this formula as previous. So we have been used d is a 5 is a thickness of the slab, and found the moment 46.88 cubic feet. And in this way we can also we can use the unbalanced moment. As previously we have been seeing the 60% of ultimate moment will be unbalanced, which is 28. But we can use this formula. The result would be remain same, as we have previously we have been seeing the 60% where. Okay, this is the test indicate this same column about 60% of the flexor. So we have flexor. The equation 60% unbalanced moment of transfer in flexor. So that's why we can use the 60% in directly. On the other hand, we can use the hand calculation also. It is depends on you. Okay. So width of the conceal beam we know C into C plus 3 is we have been found 33 inches square. So ASB within conceal beam we have been used this formula and found 1.55 inches square. So number of 12 millibar we have been used 10 bar. So our final result is there. We can see here 10 to 12 millibar at the top in 33 inches. 33 inches mean conceal beam. So not the throughout the throughout the column strip. Rather than we have been used 33 inches square, as this is the conceal beam we have been calculating. But in the column strip we have been found how much. Let me see. This is the 12 bar, 12 millibar in number of 15 bar we have been found 19 inches. On the other hand, we have been seeing the conceal beam. We have been used the 10 bar within the conceal beam. That means there is a remaining 5 bar. We have been in on 2.5, and there is a 2.5. So we can use 2.5 here and 2.5, and in this region, in the interior region or concealed region, we have been use the 10 bar, as we have been found total is 15 bar, and concealed beam is 10 bar. So we've been seen here 10 bar is we have been used in concealed bar, and here is our 2.5 bar, and top is 2.5 bar. As 2.5 bar is not used, so we can see the 3 bar is between 3 bar is bottom and 3 bar is top. Okay, let's see is number 2. Question is number 2. Here is a question number 2. We have been seen here the column strip. Uh, for the column strip, reinforcement D is exterior column figure 1. This figure also assume the all column size is given and 6 flat slab. So unbalanced moment in slab assume is equal to the ultimate moment capacity as well as the moment to be transferred flexural and shear. The ultimate shear force encases the punching failure around the exterior column. Ignore the bending moment. So punching stress around the column and considering the effect BU and MU and allowable punching stress and the story height of 10 feet and story drift is given 1 inches. Band bar and reinforcement bar around the column. So calculating here we have been found ultimate is 46.88. This is the calculating is previously and unbalanced 28 and 13. We have been also calculating here 60% of flexural and this way ultimate we know the mu equal to MUV into MB. In this way we have been found MB which is 17.75. On the other hand we can use a directly calculation as a square. We can use MUV 40% of M ultimate. So ultimate we know for 46.6 and we can use 18.7. Okay, so ultimate punching shear we know 4 into 5 into root over advance. We are taking is here 4. Why we not taking the 2? Because the compression here is a compression. That's why we are taking the 4. Okay, and found 0.21 KSA. The punching area for exterior, as we know, S equal to perimeter of tributary area and depth of the slab. So perimeter of area, this is the C, and this is the D divided by 2. This is the C and this is the D divided by 2. On the other hand, we can see this is the C, this is the D divided by and this is the D divided by 2. It will be 1D. So C plus D. So at first C divided by 3, C divided by D into 2 because in this portion and C plus D. This is C plus D and depth of the slab is given here. Okay. So and found 239 inches square. So ultimate punching shear force is BP, which is we know BU into SE and found 46.26. So we know the if we want to the punching, then we need to 46.26 keep in needed for the occurring the punching. So polar moment of inertia we have been used here for exterior column as we have been seen in previously where the this okay, this is the important. So this is the exterior and this is the interior. Okay, so we have to keep in mind this is the polar moment area, interior and exterior column. So as we see the exterior column, so that's why we are using this formula. So putting this formula and found 71.4 inch. And we are CG, which is C mix A1 A2, so A2 A3 A1 X1 into 2 A2 X2 divided by A1 into 2 into A2 and found 9.93 from X division to right. Okay, so you can see A1 is given 14.4 and 5 is how we'll get the X1 is 5. We have been found 10 divided 5 14.4 into 5. Okay, and x bar will be 14.5 divided by 2 into 2, and we've been seeing 17 into 5 and 17 is a A2. How will get the what is the ax? This is the what is the a means 14.75 into depth. The depth is given is 5 inch. That's why we are using 5, and x bar is 14.5 into divided by 2 into 2. And in this way we are seeing here 17.5 into 5. How will we get the 5? 5 is the depth of the slab. Okay, as we have been seeing here. And I am 14.5. In this way we have been calculating here, and for 9.93 from x direction to right. And punching stress, which is pp into sa divided by a, in this way, in the putting all this below, and found 0.500 ksi. That means as we have been found in previously 2.02 ksi, now it is increasing 5.00 ksi. So at first we have been found 2.0 ksi. This is the 2.0 ksi, the material strength, but it is increasingly 5.001 as punching shear around the column when we considering the calculating in calculating okay. So that was our 3. What was the answer? Number 3, punching stress around the column considering effect m. So this was our results. Okay, so number 2 results, how the ultimate punching force, this is the 46.28 ultimate punching shear. Okay, and first I have recorded. Now we'll calculate the allowing punching stress. So we can using allowable punching stress here 10 feet height and story drift 1 inch. We can see first lateral dip 3 inch, second floor 3 inch, first floor 2 inch, lateral dip 2 divided by 4, which is 1 inch dip ratio, lateral drifting percent divided by story height, and found 83 inches square. So from this drift ratio graph, as we have been seen and previously, this is the drift ratio, and shear force ratio graph. From this graph, as we have been found 83 and putting here and found, as we know the 83 is here and found 0.53, it will be like that. Okay, so by graph we've been found 83 and br 0.53 or equation. If we use the equation, the graph is not given in practically, but we are using equation, dr 0.3.5 into br. So we're putting 0.83 and found br is 0.53. So this is the best for using equation. Now we are using equation rather than graph. So allowable shear ratio will be br into dr and found 107 ksi. Okay, so these are the another tails answer. The allowable bunching shear we have been found here. So strength we have been found 201 ksi. So it will be decreasing now 0.107 ksi, and punching stress 0.201 ksi, and it is increasingly 5.506 ksi, because the drift because the concrete is cracked due to drift. That's why the concrete strength is reduced from 0.201 to 0.107. So this is 0.107 and this is 507. So this is the 0.217. At first we have been found 0.217. When we have been seen it is drift and the cracking is occurred, then it is decreased 1.7. On the other hand, when we have calculating the punching stress, so we have been seen it is the increasing 0.502. Okay, so let's see the last, which is the bent bar bend reinforcement required around the column. Okay, so allowable stress we have been found from this, and allowable shear we have been seeing get less than the punching shear. So net. Okay, so slab thickness need to be increased. So D is given here, so we've been taking 7.5, and SE we are calculating as usual, and the depth and polar moment of inner shear it is calculating here, and C is calculating here. Okay, in this way we can. Okay, so how where JG and C. So C is calculating here. Now punching stress we can calculating using this formula, and found 0.292, which is okay. Now for band bar reinforcement we can using 0.209 divided by 5 up to 0.85, and 382 using 382, and found this value, and C will be this value, and AB equal to using this formula and found 2 inch square, which is 12 bar 4 on each of the side. Okay, so here is another example we have been seen here. The figure 2 shows the fixed in column 10 height and 10 dia carried this size, and this size. This is given flat plate showing soil 1 inch due to earthquake ground motion. Calculate the superior reinforced UDL. So UDL will be calculated causes the punching shear to slab constant. Direct punching shear stress only. Direct and flexural due to eccentric punching shear and column side showing addition 1 2. Okay. So if we see there, this is the question, and this is the question we have to calculate here. Direct punching shear is stress only when calculating here AP, which is a perimeter of punching and depth of the slab we have been calculating here, and found this value. And allowable punching shear we have been used 4 into 5 into root over C AP, and found here this below. For UDL we are calculating UW into tributary area of slab minus punching area. So we know the 35.3, and we are taking the kip to pound, and W and tributary area 18 into 9, because this is 9 and this is the 18, that's why 18 into 9, and punching area pi into 2 pi d square by 4. D is we know the column dimension is 4. I will get C is given 10 and D is a 4, so C plus D is 4. C plus D is 14, and found UD equal to 219.9 pound feet square, which is PSF. So direct punching is considered. Now we'll calculate the here second one, which is direct flexural due to load and eccentric load of punching stress. So let's see here. Like cantilever we are using here WL square by watt. In this way we are putting this formula and found this, which is W into 416, and MB we know the 40% as a shear, 40% is going to torsion, and 60% is going to the moment, and found this value, and MB torsion in 185 into also. Okay, so JG for this JG is it is invented by Professor Dr. Interva Anam for circular column, and his column will be circular. This will using this JG and found this value. And allowable punching into direct shear and torsional shear we can use this formula, and in back calculation we will use W is 44.44. When you using direct and flexor, we have been found 44. On the other hand, we have been used the when we are considering only direct punching, then we have been found 419. So remember, the flexor we have been if we calculate the both, then the U will be reduced. Okay, so flexor and shear have been reduced. So we are calculating. That's why we are considering the direct punching shear. So last one we've been seeing column square side square 1 inch 1 in 2. Now we're calculating here. The allowable shear equal to direct shear and torsional shear. Putting this value here, we have been taking 0.53 and u equal to 23.6. Okay, so this is the summarize we've been seeing when we've been seeing the direct shear, direct punching. Then we have been found 219. On the other hand, and second one we have been seeing the direct and flexor we have been consider. Then the reducing 44. When we consider column sideway, then it will also reduce and 23. So this is the summary direct share only for if we consider direct share, then it will be 219. When we consider direct share plus flexor, then it will be 44. When we calculate direct share flexor plus the side share, then it will be the columns or punching will be occurred when 23.6 psi load is occurred. So this is the disaster. So this is the disaster. We can tolerate the side sway 1 inch. When we apply the 23.6, then the column will be the slab will be punch. Okay, let's see another, which is the test arrangement is 3 inch flat having area of 5 feet by 3.5 feet, supported and 3 feet height and interior RC column with 7 feet by 7 feet given in below. We've been seeing here the 5 and 3.5 is given and 3 feet is given as the ground motion is given. Calculate the force P is required to cause punching shear failure in ground column without considering drift, considering 1 inch drift earthquake. Second one is band bar required to the around of the column or the punching. Okay, let's see here. We can see here the punching shear force W equal to X into P into D, and we can see the stress equal to force per area F equal to C plus D into 2 should be 4. By punching area we will go C plus D into 2. We know the punching force into punching stress into area. As we know the stress into force per area, that's why we can use this formula from the basic. And the punching force doubling into tributary area into punching force, and punching stress we know the 4 into the reference AP here into area into AP. And we can see here we can using tributary area 3.5 into 5. This is the 5 and 3.5. And the punching area we know 7 divided by 12 into 6 divided by 12 into 2, which is C plus D into 2. As we know the C is given here. All the thickness is C is 3.7 into 7 into 7 inches is given. And in this way we are using here the tributary area with punching stress 4 into root over FMC into AP, 4 into 5.85 FMC is 3 KSI. AP is given 2 into D into C plus D, and 2 into D into CD have been found here, and W equal to 180 11.48. Punching force have been found 0.40 kip for using this formula. Now we are considering 1 inches drift, so we are equal to using this formula and found here, and punching will be 0.11 k. In previously 0.40 k, when we considering the without considering drift, then it will be failed 0.70 k. When we are considering 1 inch drift, then it will be 0.11 kip when we consider the 1 inch drift. On the other hand, last one, when we will use the band bar reinforcement required around the column to resist the punching, then we are using this the moment will be 0 because the here is column, the CG between column is the same. We have been seeing here the CG is same, and that's why moment will be 0. Okay, So and using this formula and found b equal to 0.24 keeps psi. Now using b equal to 0.24 fe and found 744 and bc equal to 36 and ab equal to 1. Now using number 3 bar, so number of band bar is required will be 10 bar. So provide 10 bar 1.3 bar in as a band bar. So let's see an last example, which is 7 inches thick of flat plate area shown in figure 3 into 4. The mode 1 is UP1 is given here. The support it is 24 into 24 columns. Assume the axial force in column is from uh, distributed load of 3 ksi and over slab length and unbalanced moment on the column is given from here, and column BMD for earthquake is given figure 4. We have to calculate the maximum shear and direct plus torsional shear in the slab around the central area. And second one, we have to calculate the longitudinal reinforcement with the conceal beam is given. So these are the given in UV model. Here is a column BMD is 150, 150, keep fit. So now we are calculating the tributary length into UTL. So 36 into 3, you have been seen here 36 into 3. As we are considering this 18 into 18, so this will be 36. And number of stories we have been seen here 10, and F equal to 4 into CD in, CD C plus D into 4 and found 7 to 0 inches square. So M equal to 150 into 150 and found 30 keep fit from BMT diagram, as we have been seen here. We have been taking a positive and negative below, and we can use directly here 60% of ultimate, or we can use this formula also. The equation, the result will be same. Okay, so now we are using ultimate equal to unbalanced into UV. So UV equal to 120. So C max equal to, we can see A1 A means C plus D into T, and we have been seeing X1 into C plus D into 2. This is the third into 2 and 4, and in this way we have been found, and J is found this below. So maximum shear is just direct shear plus torsional. We've been using this formula, which is from 1.8. And longitudinal reinforcement within conceal beam, we know the conceal beam width is C plus 3 into H and found 46. So let's see A equal to 0.3 and A is equal to 0.8 inches square. We're trying, if we give the trial again and again, then we've been found this way. And this reinforcement will provide within the conceal beam. Okay, everyone, thank you everyone for your patience. I will not longer this what I will say, um, this session, as we have been seeing the lots of the noise is coming. So that's why today's topic is ended here. If you have any question, then let me know. I hope then all the topic has covered. Thank you. Okay.